In this video, we're going to be going over our basic characteristics of acids and bases, as well as how to calculate concentration of hydrogen and hydroxide ions, as well as pH. So the first thing we're going to look at is just some general characteristics. An acid, as you know, is anything that has a pH of less than 7. And so we know on our pH scale from 0 right up until 7, so 6.9 infinite nines, right? We are an acid. And then we can further break that down into strong acids and weak acids. But anything that has that pH of less than that 7.000000 value is going to be considered an acid. So we define acids a couple of different ways. So the two ways that we're looking at in this class is the Arrhenius definition, which tells us that hydrogen ions are released into solution by acids, and the Bronsted-Lowry definition that say hydrogens will be donated by acids. So a strong acid is something that dissociates completely in water, releasing all of the H+ ions it has. And so our 6 strong acids are hydrochloric, hydrobromic, hydroiodic, nitric acid, sulfuric acid, and perchloric acid. And these ones in solution will completely dissociate into H+ and whatever other ion that they are with. Okay, so notice that chlorine, bromine, iodine are all halogens, and it should stick out to you that fluorine is not included in this list. So fluorine, think about the characteristics of fluorine, really, really small and highly electronegative. So it's going to not want to give up its hydrogen ion that it's bonded with. So fluorine, because it does not want to give up the hydrogen ion and does not want to dissociate, is not included amongst these strong acids. Okay. Then our weak acids dissociate very little in solution. About 10% is a little bit of an estimate there. The actual value is governed by the Ka value, which is not something that we cover in Chem 1, is something that is more covered in AP chemistry. But the numerical value of the Ka, the acid dissociation constant, governs how much of a particular weak acid will dissociate at a certain temperature. Every other acid other than these strong 6 would be considered a weak acid. They release very few H+ ions. So as an example, here we have acetic acid. With acetic acid, notice that it is in equilibrium, the combined form as well as the ion form. And we actually would have a higher concentration of this combined form than we would with the ion form. All right, so bases. Bases are anything that have a pH of greater than 7, so higher than 7.00, so 7.001. Anything that is higher than that exact on the nose 7 point infinite zeros would be considered a base. And just like with acids, we can break them up into strong acids and weak acids. Okay, so our definition of a base is anything that releases OHs in solution, which is our Arrhenius definition of a base. And then we also have the Bronsted-Lowry definition of a base, anything that accepts an H+ ion. And the reason being for this is there is a very common base, ammonia, NH3, which is 100% a base, but would not fit with this Arrhenius definition. NH3 has no hydroxides to release in solution, but yet it is a base. And so we have to follow the Bronsted-Lowry definition for situations like that. All right, so strong bases. Strong bases will dissociate completely in water. They will release all their OH- ions and include any of your hydroxides and oxides of 1A and 2A metals, with the exception of magnesium and beryllium, for the same reason that hydrofluoric acid is not included as a strong acid. Magnesium hydroxide and beryllium hydroxide are not included as strong bases due to the size. Our strong bases, like sodium hydroxide, dissociate completely and release the OH ion. Our weak bases dissociate very little in water, and they release very few OH ions. And just like the weak acids were governed by a Ka, Weak bases are governed by a Kb, the base dissociation constant, that tells us specifically how much would dissociate. All of your other bases, the magnesium hydroxide and the beryllium hydroxide, are examples of weak bases. And again, just like the weak acids, they exist in an equilibrium between the combined and the ion form. All right. And then that leaves us with our neutral particles. Neutral, pure water, existing at exactly a pH of 7 point infinite zeros. In neutral solutions, the concentration of the H plus and the concentration of the OH minus are exactly equal. And when we look at the value that is generated between these ions, that's going to lead us into our calculation portion of this lecture, which starts with Kw. Kw is the ion product constant for specifically water. So let's talk about how we get there. All right, so Kw and pH. So Kw is the ion product constant for water. If you look at water, we have water as a liquid that can break into its ions, auto-ionize into the two ions, H plus and OH minus. And so when you think about our conversation that we had back in equilibrium about KEQ, right? KEQ was the concentration of the ions in solution at equilibrium. And anytime we were calculating KEQ, we always made sure we left out two things. We left out liquids and we left out solids. We left out liquids and solids because they had constant volume, so therefore their concentration wouldn't change. Well, look what we have here. We have a liquid and we have two ions. And so notice when we write our Kw expression, which is the same general form as all of our K expressions, products over reactants, we only have products. We have no reactant. The reactant has been left out because it is a liquid. So we have the product ion concentrations, the ion product constant. So we've come full circle here. So in water, the concentration of the H plus and the OH ions are equal, 1.0 times 10 to the minus 7 and 1.0 times 10 to the minus 7. So the actual value of Kw is equal to 1.0 times 10 to the minus 14th. And we can use this relationship between the H plus and the OH ions to find the concentrations of those particular ions in another substance by using the value for Kw. So just a little bit more of a breakdown of that formula. Kw equals the hydrogen ion concentration. You will sometimes see this interspersed with hydronium. Notice that hydronium, H3O plus, think about it as a water with an additional hydrogen. So really we're just seeing the hydrogen ion there. So the hydrogen and the hydroxide, and those two equal this constant value of 1.0 times 10 to the minus 14. Now, if this was an AP chemistry class, I would then go on to say at 25 degrees Celsius, this is the particular value for 25 degrees Celsius. At higher or lower temperatures, this does change. For the honors level, you can just use this value at any temperature given. We don't get into the nitty-gritty of the fact that this is temperature dependent. That is something that is discussed in AP. So stay tuned if you're taking AP. All right. And so I can just take the Kw value, take whichever one of these I'm given, and solve for the other one, right? We can do that. If I'm given H plus and I need to find OH, I'm going to divide. That's going to give me OH. If I'm given OH and I need H plus, I'm going to divide by the OH. That'll give me the H plus, right? We know how to do this. What we need to figure out is how to calculate pH, because the concentration of the H plus and the OH ion isn't super instructive to us. But we know and we understand the value of pH because that's something we've been learning for a long time. So while I don't necessarily know what a H plus concentration of, say, like 3.0 times 10 to the negative 6 means, I absolutely know what a pH of 4 is. So we've got to figure out how to get from the H plus and OH minus ion concentration to pH, because that's the value that actually means something to us. So there's two methods for calculating pH, and it depends on what value I currently have parked in my calculator. The first one is what I call the direct method, where the number in my calculator when I have solved my Kw is the H plus. And so I can just take the value that I just solved for, the H plus, take the negative log of that, and that's just going to give me pH. And yay, I'm done, right? I know what the pH is at that point. I can move on. The other method is the indirect method. The indirect method is, all right, the value I just solved for from doing KW was OH. I'm going to solve for POH by taking the negative log of the OH concentration, and then 14 minus the POH gives me the pH. So the most challenging thing in this section is to know what is the number I have in my calculator and what do I do with it? Do I subtract from 14 or not? So you have to really make sure you're keeping track of what did I solve for? What is the number in my calculator so you know what to do going forward, all right? So before we get to calculating, we have one more important thing that we need to note. In pH, because we're using a logarithmic scale, our sig figs are different. These are going to follow different rules than we've ever followed before. So the total number of sig figs in your concentration, so whatever I just solved for, the H plus, the OH minus, that's going to determine the number of decimal places in my pH value. The total number of sig figs in the pH value is not what we're looking at. It's not what we're being governed by. It is the decimal places. Now, the total number absolutely matters. Obviously, you want the number to be right, but the thing we look at in terms of sig figs is only the decimal places. All right, so we'll get some of that as we work through these. So let's look at our first example. Determine the concentration of OH minus if the H plus is 4.57 times 10 to the minus 13th. Determine the pH and classify. So anytime I'm asked to find concentration, the first thing I'm going to have to do is my KW expression. So remember, and I'm not going to write this every time, but I will write it this first time. KW is the concentration of the H plus times the concentration of the OH minus, and that's equal to 1.0 times 10 to the minus 14. Now you'll see this as 1.0, you'll see this as 1, you'll see this as 1.00. It really doesn't matter. It's a constant. As long as you have the 1 and the 10 to minus 14, it doesn't matter how many zeros are included here. I will always write 1.0 because that's how I learned it. I believe on your reference packet, it just listed as 1. But again, it's a constant. It's not going to affect our sig figs anyway. So I'm looking for the OH. I have the H plus. So 1.0 times 10 to the minus 14 is equal to, I'm going to plug in my H plus, 4.57 times 10 to the minus 13th times the OH minus. So to find the OH, I'm going to divide this across. 4.57 times 10 to the minus 13. That's going to get it off that side. So remember, anytime you're dealing with scientific notation in your calculator, it's very important that you put the one that's on the bottom of your division operation in parentheses, especially so that your calculator does what you think it is going to do. You don't want it to divide by something and then multiply by something else. So make sure it goes in parentheses. All right. So it's going to spit it out. For concentration, it really needs to be in scientific notation. So I have 3 sig figs here. I'm going to put this number into scientific notation with the appropriate number of sig figs. So I should have 3, and it's going to be 2.19 times 10 to the minus 2nd molar. So that's my concentration of OH minus. Now, in my calculator currently, I have the OH minus, which means when I negative log this number that's currently parked in my calculator, it's going to give me the POH. So I'm finding my pH via the indirect method right now. Oh, and I dropped my pen. So let's take the negative log of that. POH is the negative log, and I'm going to take the whole number in my calculator, 0.0218 ... And I'm going to take that whole value. So negative log second answer, plug in that value. It gives me a POH of 1.659 and change. Then 14 minus the POH is going to give me the pH. 14 minus second answer, 12.340083. Now, here's where our weird sig fig rule comes in. 3 sig figs in my concentration is going to give me 3 decimal places. So 12 point and then decimal. 1, 2, 3, 3, 4, 0. So I'm going to circle that as my pH. And then I need to classify this. I gave you some values in your notes in terms of what numerically is in terms of pH. Classified something as strong or weak in acid or base. This is greater than 10, so this is going to be classified as a strong base, and SB is sufficient for that. All right, so let's go through and do another one like that. So same setup. Determine the OH concentration if the H plus is 1.53 times 10 to the minus fifth. Determine the pH and classify. So again, it's asking for OH concentration. We've got to go to KW. So 1.0 times 10 to the minus 14 is equal to 1.53 times 10 to the minus fifth times the OH minus, and we are going to divide by that 1.53 times 10 to the minus fifth. So 1.0 times 10 to the minus 14 divided by 1.53 times 10 to the minus fifth. All right, and let's see, 3 sig figs. So 1, 2, 3, 6.54 times 10 to the minus 10th molar is my concentration of OH minus. All right, so that's my first answer. Now I need to find the pH because this is OH. I know when I negative log it, it's going to give me POH. POH is equal to the negative log of 6.53 times 10 to the minus 10th. Negative log, second answer. And there's my POH, 9.184 and change. And 14 minus the POH is going to give me the pH. So 14 minus second answer. All right, so 4 point, I have 3 sig figs, so 3 decimal places, 8, 1, 5. So that's my pH, and this is less than 5, so it is a strong acid. All right, let's check out our next one. Determine the H plus concentration if the OH minus is 2.4 times 10 to the minus 8. Determine the pH and classify. So I'm still finding concentration, but it's important to note this time I'm finding the H plus concentration instead. So that doesn't change anything about what I do with KW, but it will change what I'm doing in terms of direct versus indirect for finding the pH. So let's handle the KW part first. 1.0 times 10 to the minus 14 is equal to H plus times 2.4 times 10 to the minus 8. So I'm going to divide to find my H plus concentration. 1.0 times 10 to the minus 14th divided by 2.4 times 10 to the minus 8. All right, and 2 sig figs, so that's going to give me an H plus concentration equal to 4.2 times 10 to the minus 7 molar. All right, now, this is where you have to pay attention. The number I just solved for is the H plus. So when I negative log it, that is pH. There is no need to subtract from 14 here. So pH is equal to the negative log of 4.16 times 10 to the minus 7, the whole number in my calculator. And that's it. I stop. Negative log, second answer. All right, I had 2 sig figs, so I need 2 decimal places, 6.38. And then in terms of classification, this is greater than 5, so this is going to be a weak acid. All right. Number 4, let's determine the H plus if the OH minus is 3.26 times 10 to the minus third. Determine the pH and classify. So same as the last one. All right, so let's take care of the finding the H plus first. 1.0 times 10 to the minus 14 is equal to H plus times 3.26 times 10 to the minus third. All right, so let's get calculations down. 1.0 times 10 to the minus 14 divided by 3.26 times 10 to the minus third. All right, 3 sig figs, so I can keep 3 here. Delta H. Concentration of H plus is equal to 3.07 times 10 to the minus 12th molar. And again, the number in my calculator is H plus. When I negative log that, that is pH. I don't need to do anything extra. Negative log, second answer. And that's going to give me, let's see, 11, and then 3 sig figs, so 3 decimal places, 513. And that is greater than 10, so that is a strong base. Okay, oops, cut that off on the side there. All right. So that's the process if you're asked to find concentration as well as pH. You can also just be asked to find pH without having to find concentration first. So it takes this KW section out, and you're only going to have to do the negative log part. Now, some people prefer just to do it the same way every time and work their way through the KW. That's fine if you fall into that category. But I am going to show you how to do it without doing concentration. So you can also solve for pH without finding concentration first. Determine the pH and classify if the concentration of OH is 6.35 times 10 to the minus 10. So if I'm just going to find pH and I'm given OH, I'm going to take this value and I'm going to negative log it. But what I have to remember is this is OH. So that means I'm going to be generating a POH value, and then I subtract from 14. So POH is equal to the negative log 6.35 times 10 to the minus 10th. So let's go ahead and type that in. Negative log 6.35 times 10 to the minus 10th. And that's going to come out to be a POH of 9.197 and change. Then 14 minus the POH gives me the pH, which in this case is 4 point, I've got 3 sig figs, so 3 decimal places, 803. So that's my pH. Less than 5 makes it a strong acid. All right, and let's do one more. All right, determine the pH and classify if the H plus is 1.37 times 10 to the minus third. So again, because this one is the H plus, when I negative log it, it's going to be pH. I don't need to do anything extra. So pH is equal to the negative log of 1.37 times 10 to the minus third. Negative log 1.37 times 10 to the minus third. And that's going to give me 3 sig figs, so 3 decimal places, 863 for my pH, less than 5, so that makes it a strong acid. Okay.